Hey loyal fans, this video will be kind of a voyage. Let me explain. Want to visit Paris? Learn French. Want to visit Berlin? Learn German. Want to visit the future? Learn computer programming. Okay, first a little history. In ancient times, teachers complained their students weren't memorizing anymore. They were reading books instead. They were cheating. More recently, students stopped learning long division. They used calculators instead. They were cheating. You may be able to see where I'm going with this. In modern times, students able to program a computer who solve problems with code are, wait for it, cheating. Another viewpoint is that we've learned how to relegate dull, repetitive processes to machines, thus freeing our minds for more creative activities. And that might be a rationalization. In this video, I teach the basics of Python, a modern computer language that's easy to learn and easy to use. By learning Python, you'll get a glimpse of how machines think, how mathematics describes reality, and how to prepare for robots that need you to tell them what to do. And make no mistake, future robots will be able to solve problems better than you. But in an historical division of labor, you'll stay relevant by knowing why the robot solves the problems it does. By learning programming, you might be able to tell the robots how to think about the world. But if not, if you only review the topic of programming, you'll acquire a perspective about computers, maybe demystify them a little bit. In this video's first section, I explain how to set up your computer. Even though I think everyone should run Linux, the setup instructions assume a Windows platform. I made this choice because there are many more Windows machines than Linux. Also, the Linux setup is much easier, and Linux users are more likely to know how to proceed on their own. Okay, enough philosophy. Let's get started. Okay, let's install Python first. Run your favorite browser and go to, I'll just erase this, just type in Python and see where it takes you, and go to downloads right here. And the most recent version will appear at the top of the list, so let's just click that. Now, as it happens, I've already downloaded Python, and to save time in this demo, I'm going to cancel this download, and I'm going to use the download that I've already downloaded. So here we go. Definitely click that option right there. Very important. Super important to have that be part of the path. To learn Python, we need to make the Windows command prompt easily accessible. So search for the command prompt. Enter CMD. While this menu is on display, click Pin to Taskbar. That'll make it more easily accessible. Confirmed. And open it up. Now that we have the command prompt open, we need to make one more change. Point to the bar at the top, right-click, Settings, and make sure that the default profile is command prompt, not Windows PowerShell. Confirmed, command prompt, and here Windows Terminal, same. And save those settings and close the setup. Okay, let's test Python in the command prompt. First step, just type the word Python. That seems to have worked, and it's showing the correct version. And these three right-pointing arrows indicate that Python is now running in what's called the immediate mode, where if you type something in, you get an immediate response. Here goes. Python, unlike some languages, uses 2 stars as an exponentiation operator. So let's try that. That is 2 to the 16th. Let's try another one. Oh boy. 2 raised to the 256th power. By the way, this shows the existence of a recent Python enhancement called long integers. If you type in an operator that requires the existence of many, many decimal places, Python just provides them. Let's try another test here. I'm going to type in 9 ones, 1, 2, 3, 4, 5, 6, 7, 8, 9, and square that. That's a cute number, isn't it? Okay, now for our first Python program. Not much of a program, but it worked. So basically what we've established is that Python has been installed and it's working correctly. So we can go ahead. Let's make a new directory for Python programs. Open a File Explorer, go to your Documents directory, and create a folder. I'm going to call mine Python Programs. Any name's fine. This will be our storage place for the Python programs we'll be writing. In this tutorial, we'll be using a terrific, free, open source, cross-platform programming environment called VS Code. Open a browser and enter VS Code. And I think, yeah, here we go. There's a download link. Choose the appropriate to your platform. Since I'm on Windows at the moment, I'll click this one. Now, as it happens, as before, I've already downloaded the setup package, so I'm going to skip this download and use the package I've already downloaded. And accept the agreement. One of many thousands of agreements that I accept without reading them. And most of the defaults are fine, but be careful about this one. Create a desktop icon and make sure, as with Python itself, that it's attached to the path, the system path. Otherwise, you won't be able to use its name in various contexts where it's needed to know where it's located. So go ahead and start the installation. Skip that for the moment. Okay, installed. Okay, here's some VS Code setup steps, which are the same regardless of one's platform. Run VS Code. Go to the extensions icon. And the first extension I want to try is the default Python extension, which provides a bunch of useful tutorial and programming aids. Go ahead and install that. Okay, installed. Now we'll install something called Code Runner, which there's a whole bunch of copycats that are out there. Don't be deceived. Look for this orange icon right here. And I've installed Code Runner already. So now we can move ahead to some settings. To go to settings, the shortcut Control Comma. Now that we have Code Runner installed, I'm going to make a couple of settings for it. Use that search string for Code Runner save. Make sure that save file before run has been checked. Clear. super important. When you use CodeRunner to run code in a terminal, it's very desirable to clear the terminal of prior input. So make sure this is also checked. Clear previous output. One more setting. A new feature of VS Code, and to some extent it's a feature of Python, although Python itself doesn't honor the type checking notations. But VS Code does, and it makes your programs a lot easier to read and understand later. I've chosen strict. You can go from off all the way to strict. The programs that I'll be presenting in this tutorial all pass the strict standard, but if you get into difficulties and want to do away with type checking for the moment, just go to this search, type check, Python type checking, and select off. Wait until later to enable the strict version. Now to write our first Python program. Run VS Code and select Open Folder, this option right here. Choose the folder we created before for Python programs. And now select New File. We'll create a program file. Enter Hello World, followed by the suffix py, which is very important to remember. That's the standard Python program suffix. At this point, VS Code has the file open and is ready to receive our entries for this program. Notice the flyout. This is information VS Code is providing that at the moment will seem very confusing, but eventually will be very useful to help writing Python programs. Now to run the program, I have some choices. I can press this little arrow over here, or I can use the shortcut, which is Control-Alt-N. I'll just press this one for the moment. Now I'm going to use the shortcut, see whether the shortcut's working. Yes. And the terminal, which shows the output from the program, is at the bottom of the screen. I personally prefer it to be at the right. Use your own judgment, but to make the change, point at the bar at the top of the terminal, right-click, panel position. I'm going to choose right. That seems useful. And let's just run the program again. I'm using the shortcut. Appears to be working. Oh, I see I have a typo. By the way, notice something. As soon as I make a change, this little white circle indicates that the file is unsaved. But because of the configuration changes we made earlier, if we run the program, it automatically saves it. That's important to remember. Okay, that's our first program. Now to learn a little Python. Be prepared to pause the video at times to look at code listings or to absorb new ideas. If you have a choice of display resolutions, use the best available. This lets you clearly see the code listings. Okay, here we go. In this first session, I'll show some more VS Code settings, then cover some basic programming issues. First, notice the keyboard display at the lower right. This allows you to track what keys I'm pressing. Next, I want to increase the display scale for this tutorial. I changed VS Code's display font by pressing Ctrl+ to increase the font size and Ctrl- to decrease it. This is okay for small code samples, but later on I'll have to pack more code into the display. Here's another useful CodeRunner setting. I want to eliminate the brown text appears before and after the running program's output. So to start, press Control, and type CodeRunner execution. And disable this option. Disable show execution message. Remember this setting in case you have to change it back. In Python, program logic is controlled by indentation. In older languages like C++, braces govern program logic, and indentation has no actual meaning. Don't worry, I won't dwell on C++ very long. This is just for an example. If I run this program with the present logical settings, I see that state A is set to true, so I get that printed, but state B is false, so state B doesn't get executed, and because state C is nested within state B, it also doesn't get executed. And if I flatten all these indentations, it has no effect on the program. It still runs the same, just like that. Because in C++, the structure of the program is governed by braces, and indentation is simply a convenience for the programmer. It has no actual syntactic significance. By contrast, in Python, program structure is controlled entirely by indentation. This makes it easy to write Python programs, but if indentation gets changed by mistake, debugging can be tricky. At the moment, this program's logic is parallel. Each true logical state prints something. For example, state A is true, so the state A sentence gets printed. State C is true, so the state C sentence is printed. But I can change the logical structure of the program by changing the indentation, like so. Unlike in C++, I just changed the meaning of the program by changing the indentation. This is very important to understand. Now it's back to parallel again. Remember this about Python programs. Indentation is everything. A missing space can bring a Python program to its metaphorical knees. Also, for indentation, use spaces, not tabs. There's a long online debate about this topic, but use spaces. VS Code defaults to spaces. When you press the tab key, VS Code emits a series of spaces. A little demo here. I'm pressing the tab key, and you can see it with spaces. In most cases, VS Code will tell you if you have the wrong indentation. The line after a colon is expected to be indented to reflect the meaning of the colon. And if I thwart that, if I deliberately remove one, VS Code will pop a message, an error message, expected indented block. VS Code is very handholdy that way. It'll tell you whether you make an obvious syntactic error of that kind. Let's look at ways to make a program execute a loop, a repetition. A typical Python loop can be gotten using a range, which is a convenient way to get a sequence of numbers. The minimum arguments that can be provided to a range are a single number, which defines the endpoint for the endpoint minus 1 for the range provided. If I add more arguments, I get different results. Here's an example with a starting point as well as an ending point. So you see how the starting point changed. The third argument, the third optional argument, is a step size. So let me see if I can make a suitable range for some purposes. So, okay, what we have now are the three arguments: an optional starting point, a mandatory ending point, and an optional step size for each of the arguments. Now let's make a loop. Okay, now we have a nicely formatted list. Let's try to add some things just for fun. Let me move this over a little bit. Okay, we have that easy enough to do that. Now we'll try something else. I need more room. Okay, that's fine. I chose the left-hand argument here. By the way, this is something called an F string, a very powerful feature of Python. In this particular example, I'm saying that I want a field size, an overall field size of 22 characters, and I want 16 decimal places to the right of the decimal point, and the result is a floating point, expected a floating point argument, which the square root of n frequently is. Not always, but usually. And so I'm looking at the square root of 2. Yeah, that looks correct, actually. So that's a simple enough loop. There are other ways to make a loop, which I'll show next. There are more ways to create a loop in Python. Ranges are just one. Here's a loop that uses the keyword while, which repeats until a specified condition is met. I'm going to write this example to reveal an important property of computer floating point numbers. One might even say a vulnerability. Here we go. Oh, that's funny. What this while statement means is that if n equals 0, or n is equal to 1 or greater, the loop should exit. But n was equal to 0 right here, but nothing happened. It didn't exit. As to why it didn't exit, that's going to take some telling. Here we go. I'm going to increase the number of decimal places to 16. And surprise, surprise, it turns out that n never exactly equaled 0, which is why this test failed. This results from the fact that floating point numbers, even though they're displayed using base 10, they're processed internally in base 2. This can cause issues with specific numerical values. And as it happens, adding 0.1 to a floating point number is a particular case. For integers, numbers with no fractional part, there's no important difference between decimal and binary numbers. They're essentially equivalent. But for floating point numbers, they differ, and in non-intuitive ways. So the rule is, don't expect a floating point number to exactly equal any given value, or avoid using floating point values as loop indices, and instead derive floating point results from integers or floating point numbers that have no fractional parts. Short version, never use floating point numbers as loop indices. Here's a solution, by the way. I got the same result using integers as loop indices, and I derived my fractional floating point number from the integer. So the reason this worked and the prior example didn't work was because these are all integer operations that control the loop, including this comparison. So that's the rule. Don't use floating point numbers, at least floating point numbers with fractional parts. This is something that arises with experience in programming. This is a small Python program that prints a multiplication table. To save a lot of typing, viewers may acquire this file from this internet address. Here's a function named multtable that creates the table. Because this is a tutorial, it has many more comments than a typical Python function. To create this program, I declared a Python function starting with the keyword def, meaning define, followed by the function name multtable. This function accepts an optional numeric argument, but if one isn't provided, a default value of 12 is used instead. The colon at the end of the function declaration marks the beginning of the function's control block, and the following block must be indented to mark its scope. If we remove the indentation, VS Code immediately detects and displays an error message, expected indented block. This is one reason why VS Code is such a useful Python environment. It gives immediate feedback as you type and flags obvious syntax errors. Remember this rule. Python control blocks are identified by a colon followed by an indentation, and if that indentation is removed, the program loses essential structure and cannot function. The next code line creates table rows by assigning sequential numeric values to variable y, and all the code lines below it are within its control block, these lines. The next code line creates table columns in much the same way, and a single code line lies within the control block. This code line prints columns of data, each the product of x plus 1 and y plus 1, and is configured not to create a line feed, which is what this does here. So it creates as many data columns as required. This code block ends each data row with an actual line feed, right here. Now let's try running this program, see what happens, or more to the point, what doesn't happen. Nothing happens. The reason nothing happened is because the function has been declared but hasn't been called. Remember about Python functions that they are code blocks that await being activated from elsewhere in the program. They can't function on their own. So I'll just uncomment these other lines. Now, with the same command, that's our first example of the table. I mentioned before that the default value is used if no argument is provided. If I do provide an argument, it's used instead. Now here we are for 16 by 16. And a little larger, 20 by 20. That's our multiplication matrix, and it's a very simple program, does something people might find useful. This program shows more advanced Python features, including an enumeration class whose purpose is to clearly specify program states, right here. Let me add these programs are available at this internet address. I want to make sure I've covered the terminal location issue. In this example, the terminal is located at the bottom of the display and hides some of the code. But for this tutorial, the terminal should really be at the right. To solve this, point at the terminal top bar, right-click, panel position, right. That's better. The purpose of this program is to map weekdays to scheduled events in a function called activities. This example just prints a message each day, but the activities function could just as easily carry out actions appropriate to a given day. The activities function uses the relatively new Python match case control scheme to map weekdays to event control blocks. The advantages of an enumeration is that it gives the program a fixed set of defined states with easily understood names with no ambiguity or chance for confusion. Older programs used numerical values instead of defined labels. Such programs were more confusing and error-prone. Notice the default case statement with the underscore. This is an error-trapping case whose purpose is to alert the programmer that an unassigned code has been received. For testing, I included a non-existent weekday in the enumeration to make sure the error trapping actually works. Also notice that the activities function identifies the input data type and the return type. This is an example of data typing, a desirable practice as programs become more complex and more reliability is required. As mentioned previously, we can make VS Code alert us that a variable or function isn't correctly typed. How about a digression? A little digression about Python type checking. Enter control comma and enter Python type checking. You have the choice of using the strict version or no type checking at all, your choice. As you learn Python, it might be desirable to turn off this feature to avoid some annoying messages and only gradually increase the level of checking. Your call. Compared to match case, there are more efficient ways to map a program state to an action. For example, a Python dictionary, which this is an example, with states as keys and actions as values. A Python dictionary is a kind of array with key indices instead of index numbers. The advantage to a dictionary is the program will reject a non-existent key. The program will stop and print an error message. Here's a short example program to focus in on the dictionary feature. Notice that if a non-existent key is used, an error results and the program halts. I have a non-existent key deliberately introduced into the key set to trigger this error. But we can use the try except approach to avoid stopping the program. If I use try except and run the program continues to run. It just prints an error message for the non-existent keys, but allows the program to continue to run. Going back now to the weekday program, Activities B uses a dictionary instead of match case, and it runs more quickly and is more concise. My point here is that a program can take many forms and produce the same results, and the best approach to use depends on the program and the goal. In this example, I show how to manipulate character strings and lists. Let's go step by step. First, I create a string of words. Then I create a lowercase version of that word string. Then I create a list of the words by breaking the string up into individual words. Then I sort the list. Then I search for individual letters within the words and print the results. Here goes, we're running the program. Notice about this example that I use meaningful variable names throughout. This has two advantages. One, a month from now, I'll be able to understand my own code. Two, someone else might be able to understand my code. Both are advantages. Here's a more advanced example that reads a large English dictionary file, then looks for words that match a provided search argument. The program starts by reading a dictionary file, then makes all the words lowercase, then splits the word list into individual list entries, all in one code line. Then the program submits the word list to a search algorithm and creates a list of matches, all in 2 code lines. Then the program prints the results using a somewhat exotic print function that I have collapsed right now to keep this display from being unreadable. Here, let me uncollapse it. The print formatter displays its results in alphabetically sorted columns, more or less like an old-fashioned telephone book, meaning sequenced first by rows, then by columns. Here's an example. Rows, then columns. Counterintuitively, the print formatter prints columns in the inner loop, then rows in the outer loop, but this is done in such a way that preserves the row priority of the alphabetic sort. Notice about this F string that its width specifier is a variable called max column width, defined earlier in the function. This is a nice feature of Python F strings, not present in other languages. It lets me set the column width dynamically based on the longest word to be printed. This program can be addictive. I find myself searching for all kinds of exotic words. Wow. This program has another mode. It can find palindromes, words that read the same forward and backward. To switch modes, I just call the main function with a true argument. So this is a list of palindromes that have 6 or more characters in their lengths, quite a few. Let's make a longer list. Let's try 4. Wow. Considering the size of the dictionary, I'm impressed by how many palindromes there are. Let's try 3. Wow. Okay, let's go back up. 7. There's only 17 of those. And 8. Only 2 palindromes in this giant dictionary with 8 characters. And both of them are actual words. They're not just made-up words. One is a name of a plant here in the northwest part of the U.S. The other one is a language in India, one of the many registered languages in India. How about that? Most modern computer languages support something called a class. A class is a sort of package of data and functions that operate on the data. Remember the distinction between a class and an instance of a class. A class is defined once, then we create instances of that class with specific data to accomplish a purpose where the data and the class functions work together. A special class function called init receives data and creates an instance of the class with that data. Within the class, a special term called self refers to a specific instance of the class. Each class function receives, as its first argument, a reference to the instance called self. Remember that class functions operate on an instance of the class. Class functions can call other class functions using the self keyword. In this example, I create a triangle class to show a relationship between data, the triangle's dimensions, and class functions that operate on that data. The purpose of this example class is to describe the triangle described by the provided data. For example, what is its perimeter and area, and is it a Pythagorean triple? There's actually a simpler way to identify a Pythagorean triple, but I wanted to create more class functions and show how they interact. In the function triangle tests, I traverse a list of triangle values, datasets, create instances of the triangle class, and display some results. I chose this example because without a class to organize things, much more code would be required to process the numbers and create the results provided by the triangle class. Another class example would be a planet class, one I find myself writing over and over, where each instance is a solar system planet or moon, and the instances are processed together in a solar system numerical model that predicts future planetary positions. This is a somewhat more complex program, an RPN calculator. This example is more than a lesson, it's actually useful. The source is on my website, link at the top here, and in the program notes. RPN stands for Reverse Polish Notation, a clever scheme that does away with parentheses in mathematical expressions. The Hewlett-Packard Company makes RPN calculators that are popular with engineers and scientists. Before I describe the code, let me show an example of an RPN calculation. Viewers may know that the length of the hypotenuse of a triangle is the square root of the sum of the squares of the other two sides. For this example, let's use a well-known Pythagorean triple, a triangle whose sides are all integers and that have a certain relationship. Example, 3, 4, 5. I'll use the two known sides, 3 and 4, to calculate the hypotenuse, the third side. The conventional mathematical solution uses parentheses, but this is how I would do it in RPN. I warn my viewers that RPN calculators can become an unbreakable habit. Here we go. That's the hypotenuse. Notice I didn't use any parentheses. Good thing too, because this program doesn't have any. Now let's look at the code. The class starts by declaring a stack of floats and a label string to identify the stack's contents. The exec function is the primary function, does everything. The first action the program takes is to show the stack if there are any stack contents. Then it accepts a user input. That user input is then broken up into tokens in case the user has entered more than one command separated by spaces. Each of those arguments is then processed separately. The first thing the program tries is to convert the token into a number. If this succeeds, valid is set to true, and all the rest of the possible commands are skipped. If the entry is not a number, the try except clause will set valid to false, and we move on to another part of the program. Assuming the valid flag is still false, and there's two arguments on the stack, the two argument commands are tested. If the token isn't in that list, the one argument list is tried next. If that fails, the program compares the input to a list of constants, or a quit command. If all the tests fail, an error message is printed and the program accepts a new command. This means the valid flag tracks the program state, and if no valid results are found, the program prints an error message and then accepts a new entry. I created this example to show how quickly a Python program can become more complex and more useful. For the next section of this video, I need to explain about prime numbers. Here we go. A prime number is a number greater than 1 that can only be divided by itself and 1. Numbers that don't have this property are called composite, meaning composed of primes. A prime sieve is an efficient way to locate prime numbers. It's a list of numbers that can be marked as either prime or composite. In a sieve, We begin by assuming all numbers greater than 1 are prime. Then we run tests, starting by accepting 2 as prime. Because all multiples of 2 are divisible by 2, they're marked as composite. This makes 2 the only even prime. Continuing to the right, 3 is accepted as prime. All multiples of 3 are divisible by 3 and are therefore composite. The tests continue. All numbers not already marked as composite are prime, and all their multiples are marked as composite. Modern prime sieves are much larger than this example. Some have billions of entries. Okay, now we can transition back from theory to code. At this point, you should be familiar with the ideas behind prime numbers and the prime sieve, so I can describe this code in some technical depth. The size of the prime sieve is provided by the function argument top. I first create a sieve of Boolean values of that size, all initially set to true. I then create an array to contain the prime numbers the sieve locates. This array is returned to the function caller. I've added a few optimizations to speed up this search. One optimization is to examine only odd numbers. This cuts the search time in half. But that means I need to put the only even prime, number 2, in the prime list. Another optimization is that the algorithm only needs to search between 3 and the square root of the sieve size. This optimization means there must be 2 loops. One searches from 3 to the square root of the sieve size, striking off composite numbers as it goes. The other loop gathers the prime numbers located between that partition and the full sieve size. In the main function, I call 2 sieve functions, my sieve function and the one provided by the Python SymPy library. The point is to compare my optimized function with a standard library function with the same purpose. Now let's run the code and compare the outcomes. Here we go. It turns out that while searching the first million integers for primes, my algorithm is over 130% faster than the Python library, sieve, more than twice as fast. The printed summary shows that the prime lists are the same. Both functions generate exactly the same primes. I should emphasize that there are many more optimizations applied to prime searches. Those described here are just the obvious ones. I haven't mentioned this yet, but Python is an interpreted language. It trades speed for convenience. For comparison, I wrote a similar prime search algorithm in a language called Rust, a very fast compiled language. This version doesn't have all the optimizations I applied to the Python code. Let's run this Rust version to see how much time it takes. Here goes. Okay, wow. This code needs less than 2 milliseconds to produce the same results Python created in 35 milliseconds. This makes Rust over 20 times faster than Python. I wasn't planning to editorialize, but after you learn Python and become adept at code creation, then learn Rust. Here are some F-string formatting examples. Let me run this example to show the outcomes at the right. Here we go. First is an example that breaks long numbers into groups of 3, separated by a comma, but the separating character can be chosen based on locale. Next is an example of text justification, left, right, center, with specified field width inserted into the formatting string. Next are some date and time formatting examples with different formatting specifiers inserted into the F-string. Next is another example that inserts a variable into the F-string format specifier, this time to control the number of printed decimal places in a float. Finally, an example that displays a list of Python entities and their types. Pretty nice. Notice about this example that A, I have strict Python type checking enabled, and B, the type checker can't decide what type to assign to my eclectic list of Python types. This means one can't always make the type checker happy. F-strings are a relatively new, powerful Python feature, one that makes older formatting methods seem crude. Hey, I hope this tutorial met your expectations, and if I missed something you wanted to learn, please tell me in the comments. Because I'm planning more Python videos, I'm ready to add any topics I missed this time around. Here's a prime sieve written as a web page, just to show how the algorithm works. Some of you may know that prime numbers lie at the heart of modern computer security. This is because multiplying two large prime numbers together is easy, but finding the primes in the result, a process called factoring, is a famously difficult process. The difference between creating and factoring large composite numbers is a key idea in modern computer security. Some speculate that quantum computers might make factorization easy, which if true would demolish modern security. But others say this can't happen. At the moment, it's an open question. Here's a mathematical object called a Hilbert curve, a fractal curve that blurs the distinction between dimensions. Even though the curve is created with a one-dimensional line, because of its fractal nature, it challenges the concept of dimensions and eventually covers a two-dimensional plane. This Hilbert curve generator is written in Python with a little help from complex numbers. I hope you've enjoyed this video. Again, if I missed your favorite Python topic, please tell me in the comments.